Yes. There is a small change on schedule. Today, Donggun Kim will have a lecture, second lecture, instead of Jin. They switch each other because of the schedule of Donggun. And then today I prepared a small experiment, so maybe we should delay our session to next time. And then another one is 26. I have a travel, so that it should move down to evening class on Tuesday. So there will be 2 classes on instead of 26. On Thursday, next week, morning time, there will be no class because of my schedule. I will send you this revised one. Right, so any other questions? Yeah.
Isn't 31 holiday? Is it
Now
holiday on 31? On the 31st, isn't it holiday?
Holiday. Oh, what? Korean?
I think it's the first.
The voting.
Yeah, probably.
Is the first.
Oh, first.
You're right. Let me see.
Because I was told in a previous class that, not this class, but another class.
Okay. So Wednesday is holiday.
Yep.
Other questions? No. And we can move on to this material. Let's see. Surveillance. Right. So we move on to this book, second or first textbook. Chapter is on static stability. And next chapter is dynamics. So we'll see what is the difference between static and dynamics. And buoyancy and hydrostatics, fluid mechanics. Have you attended any class on fluid mechanics before? Most of you. So it can be just a reminder of some basics. Pressure, also taught in fluid mechanics. Buoyancy, maybe not, right? In fluid mechanics, maybe a little bit. So fluid is what? Deforms and liquid and gases. So fluid and liquid is not the same. So fluid is more bigger concept than liquid. There is a plasma, gas, and plastic. So in aerospace engineering, they are saying aerodynamics. It's a gas dynamics. And in naval architecture and marine engineering, they are saying hydrodynamics. It's something like water dynamics, hydrodynamics. Fluid dynamics is wider scope. All right. And solid and fluid, you already see that. Solid deforms also, but not change indefinitely. Fluid cannot resist deformation force. So change continuously. That is the difference, main difference. You already see this one before. Just remind you, density is a mass per volume, simply kilogram per cubic meter. And temperature and pressure make it change the density. Typically, air, fresh water, seawater. See, you see that 1,000 times higher density than air. And also fresh water and seawater, there is a small difference. That gives you, when you design a ship, the ship can travel to inland lake and also ocean. There is a case that in China, Shanghai is a end point of the long river. What's the name of the river? Changgang, Yangtze River. Yangtze River is very long. So in China, there's a big two rivers, and there is a ship through the Yangtze River up to, there's a big dam over there, probably largest dam in the world. Shanxi Dam, Samhyuk Dam in Korea. So the ships are traveling over the dam and also down to the Shanghai, and then travel to sometimes into the Korea. So that kind of ship is not big because they should travel through the river and also through the gate of the dam. But they should travel. But see, because of density difference, the submergency of the ship, the draft, is changing with the same cargo inside. And viscosity, also the resistance of deformation. We saying thick fluid. So there is a thick fluid that cannot flow, right? Water is thin, but honey is thick. Pressure is a Pascal, right? Newton per square meter. And the force per unit area. So sometimes not weight, but weight to ratio something. Right? And then there is a bar. Bar is for air pressure something, right? And then PSI, pounds per square inch. So standard atmospheric pressure is 1 bar. Right? But in Pascal, it is a little bit different numbers. In fluid pressure, but fluid including gases, air, right? Fluid is larger concept. Is a fluid density, gravity constant, and height. Same as in ship, or also in the air. The pressure depending on the height of the fluid. Right? As I told you before, when we climb up to the Himalaya mountain, 3,000, 8,000 up, the water boils under the 100 degrees, right? Because of the pressure is low. Why pressure is low? The depth of the air above us is smaller. Same reason, the ship, the ocean, you go down to the deeper water, the pressure is going up because of the weight of the water above you. As I told you before, 10 meter per 1 bar is increasing. Right? So if you say 100 meter, 11 bar. Right? It's a very high pressure. And that gives you differences in force. Big ships, the draft can be 20 meters, 30 meters. And in several capsizing of several ferry of Korean disaster, the water depth at the ship sank, it was 40 meters. So it was not easy for divers. Right. Liquid and gases. So fluid includes liquid and gas. And pressure is quite different because the density is 1,000 times. And also the property compressibility. Compressibility is goes to gases, aerodynamics. So airplane, they should handle the compressibility. Practically, water also compress, but it is negligible. So we usually say for the calculation, simulation, equation, we assume that water is incompressed because the equation becomes very simple if you delete terms about compressibility. So aerodynamics need to handle that portion. So hydrodynamics and aerodynamics. For the ocean engineering, for the aerospace engineering, they use, this is inside the fluid dynamics, right? They are specialized in air and similar, but not quite the same. So density is 1,000 times, and compressibility, yeah, nearly incompressed. And free surface. Free surface, see here is the wave behind the ship is running. Okay? The free surface is between air and water. We call this is free surface. Because of due to the density difference of 1,000 times, there is a change. Free surface. It looks like a free surface, but this one is a shock wave. Buoyancy. This is the most important one for this class. There is always we have a equilibrium between weight and buoyancy. This is a ship. This is a ship, right? Made of steel plates. Inside empty, almost same as ship. But the steel plate is floating. Right? Floating. But this one has their own weight. We call this is a lightweight of the ship. Basically, the ship has more because engine is inside, bed is inside, a boiler is inside, more. But simplified it is same. Okay? So lightweight of the ship. So there is a very shallow draft. Now it is equilibrium between weight and buoyancy. Buoyancy comes from where? Why buoyancy? Where buoyancy comes from? This integration of pressure coming from the water towards the structure. Why? Because the structure displaces the water. If you push down, I need to press more force down. Right? So there should be a balance between my force and then weight together. And then the response force is buoyancy. And buoyancy is an integral of pressures all over the surface. Now, see, when I drop down in this way, this is the dynamics. But when the water is come down, you can say this is statics. So you can measure the drift when it is come down. Right? Dynamics is complicated, right? Changing, motion. Right? So the equation is complicated. So buoyancy is upward force exerted by fluid, right? Fluid that balance the object weight. So weight should be same as buoyancy. So balanced equilibrium. Weight of the object, it comes from density. Right? So density, gravity is going, this force comes from gravity force. But this is balanced by displaced by using of integral of pressure. all over the surface. But complication again, the pressure level is different. Pressure level is different because of the depth of the water. If this depth is 30 meter, the pressure here is 3 times higher than here, or 4 times higher, 3 times higher. So integration of pressure over the surface is not easy. You need to have a computer calculation. By hand, it's not impossible, but it's very hard work. But when I was young, there was no computer. We should do that by hands. Or small calculator. Hydrostatics. buoyancy applied to an object. And pressure. Pressure is different because of the depth of the water. But anyway, equal volume solid object. And that how much of the buoyancy of this object is applied is this kind of integration of pressure over the surface. But because it looks like this weight of this object is bigger than the weight of the water is the same amount. The displaced water, amount of displaced water, that amount of weight of the water is the buoyancy. But still, the object is inside the water. Right. So hydrostatic spring. So we usually saying this buoyancy looks like a hydrostatic or static spring. You know about the spring forces. Spring forces Kx. Same as when you push down more, the response force is higher. Right? So it's push down, more response force. Push down. So we can say this is a, and also looks like when there is a spring is released, then there is a cyclic motion. Spring is then pressure. Pressure is all over the force equilibrium and then integration over the surface of pressure. Once again, static fluid. If you have a hole of 2 different points over the surface, the shape of the water flowing is different. Because what? Because the pressure at this point is different. And pressure difference comes from the depth of the water. That's why say all over, but in one point, single point, the pressure is same all over the direction. Let's notice. Single point at any point, the pressure is all over the direction is same size. Here and here, very small difference. But one single point, ideally a single point, should be same. Pressure increase with the depth in all directions, equally all directions. And then pressure at perpendicular to the surface. Now let me see this. But this one is say hull of the ship. If this is a portion of the ship hull, and then pressure increase as a water depth, but you need to have a designing this ship structure strong enough. Then you should know that the plate thickness of this ship should be different along the depth. You need to have a thicker plate to withstand the higher pressure. if you say this one is 30 meter, then pressure is 3 times higher here. So plate thickness should be different. So this is loading. Loading of cargo onto the ship. As we expect, the direct increase. At the center of the buoyancy. And if we put the draft and then freeboard is here, freeboard. Otherwise, if you have a very small freeboard, then the ship is very natural, very natural. But you see, we did not think about this kind of phenomenon. More details. One more single question. This is a new bottle brought by the new bottle. So when I put this one inside the box, what is your expectation? It will be floating or sinking down to the bottom. You have choice. Floating, sinking down to the bottom. Split. Eh? Let's try this. Let's try this. Floating. Sometimes it is going down. So because of probably small gap air here. So that I will try another experiment here. I need to fill it up all over the water. No air gap there. So what is the expectation now? Floating, still floating, still floating, going down to the bottom. Let's try. Not coming. So sometimes it is floating, sometimes. I tried it this experiment many times. What is the difference between sometimes it is floating, sometimes this time it is going down?
The amount of plastic?
Right. Density of this plastic gives you a difference. But as I told you before that, oh, there is more air still there, but still it's going down. Your body is very similar to this. Your body, the density of your body. As I told you that if your lung is full of air, then it will be floating. No air inside the air, or small air, and go down. Right? That is a small experiment. So hydrostatic and buoyancy is and pressure. And submerged body. That is a submarine, right? Submarine. Fully submerged. That should be neutral, means the weight should be very similar to this one. You need to make this submarine work as a neutral buoyancy. Otherwise, submarine go down. All floating. If your submarine is floating, enemy find out your submarine, so you need to submerge, but too heavy, going down. Right? So neutral buoyancy is important for the submarine. So how can you control this? You need to have a air bubble generator and also some void rooms that you can control to fill in the water or fill in with the air by controlling the temperatures, air generator. We call this is a ballast tank. Ballast tank. Every ship especially for the submarine, they need to have several places of small ballast tanks and then control pumps. So the captain needs to control the switch to pumping out, pumping in water and air throughout the ballast pump because weight is changing. Right? Ship can be this way, or this way, or this way. Because of the people are moving, water is drinking, and fuel is consumption. And so captain needs to have a control. And also neutral buoyancy is not easy to control, not easy to keep. So you need to have a control. And sometimes submarine floating. Iceberg. This one is what looks like an iceberg. Also, your body is like an iceberg when your lung is full of air. So 90% is under the water. Submarine, how to dive and surface then? Right? This one is, you see, there is two hulls actually. We call this as pressure hull. That is important. And outside there is another layer that is not so strong. This one is very strong because yourself is inside here. So this steel plate should be thick enough, right? But thick is heavy. So by you controlling the ballast tanks over the submarine, you need to make it neutral buoyancy or more buoyancy, more floating. So let's see the video here, how the submarine is working. What is it? This one?
They can reach depths of about 800 feet thanks to a system of internal and external ballast tanks.
We have 5 external ballast tanks, normally filled with air when I'm riding on the surface. When it is time for us to dive, we'll open vents on those ballast tanks. There's grates on the bottom of the ship that allow water to come in, displace the air, making the ship just slightly negatively buoyant. We then proceed down to the depth that we want to go to. And we use internal ballast tanks to make the ship neutrally buoyant, that then we can progress on our way in whatever depth we choose.
The crew on board the Virginia class have an abundance of cutting-edge controls at their fingertips, one of which is replacing the most iconic feature in submarine history. The periscope has been a key component on the submarine for over 100 years, but engineers on the Virginia class are taking a bold step toward the future by replacing the periscope with a state-of-the-art photonic mast.
The photonic system is a mast with a sophisticated camera system that allows what would normally be displayed just in a periscope to be displayed on widescreen monitors throughout the ship.
And it used to have an optical periscope that came down, which drove the construction of the submarine and the orientation of all of the rooms on the submarine.
Bulky periscopes force most submarine control rooms to be located on a cramped upper deck. On the Virginia class, the compact imaging equipment is housed in a part of the submarine known as the sail. This allows the sub's control room to be built on the wider second deck.
My control room that I'm standing in right now houses all of the important decision makers. It really brings the crew together to operate as a team, as a unit.
stability. So there are three states: stable, neutral, and unstable. As I told you before, you can make this a stand here. When I use some disturbance, collapse. You need a very small, but how small is different. But you need a small disturbance. When still with this unstable system, So when we put a very small disturbance, then stable system move somewhere, but this one can be returned back to the original system, original position. We call this is a stable system. Neutral, no change, still there, stay there, right? No return back, no return back. Unstable, start falling down, right? Cannot return back to the original. So simple three-state of stability. Any system, right? Including ship. So stability of ship is very important. Stability of ship. Did not bring. This one is submarine model. So this one, I need to have one more cap here. What to do? When I have a disturbance, oh, there is a weight. Opposed to weight is down. This stable. It's returning back to the original position because of this heavy weight in here. Heavy weight down there. Right. Stability. Need to have a high weight at the bottom side. So ship must be sufficiently stable because ship should pass through the very bad water, high waves. Otherwise, capsize. That has happened to several times, 8 years ago. So when statically stable, also dynamically stable. In this chapter, we are talking about static stability first. Floating upright. This one is floating upright when at rest in still water. And return to its initial upright position if given a slight temporary deflection to either side or disturbance. Or sometimes there is a neutrally stable. So this one is stable because of the high weight at the bottom, so that when I make you disturbance, you're returning back to the original position, upright position. Return to its initial upright position. That is a safe ship, right? Stable ship. Otherwise, it capsizes. So very similar to this one, because you may not have experience with the ship. When you see, you probably have a experience to see such a truck. Overloaded truck. Looks like unstable, huh? Unstable. Do you have a driving license? All right. So you know how to drive a car. When you have this kind of car driving, if you need to turn, then you need to, at a normal car, you need to slow down when you're curving. Right? But this case should be more sensitive. Right? Unstable. This one is unstable. Right? Because of the CG, center of gravity, is high. And I am saying that Seoul has very similar cases. So otherwise, careful turning, otherwise should capsize. All right. Question. No question. And Yeah. So already I finished my experiment. Then we may continue on second lecture, right, Donggun?